This is a quick covering of the math of a one-way speed of light. When I started with what would a faster than light traveler look like to a stationary observer, given that light propagates through space at a constant speed, light originates in space at some point of emission, the direction and speed of the emitter does not change the speed of light, and the observer is some distance from the path of the traveler. So we have an observer here and something that's moving very fast, and it's going to take some amount of time for the light from various emission points to reach the observer. So there's a distance from the path of the traveler, which is going to be straight across the screen, and that's d. And then I use 3 points along the body being observed to track how big it is, where it is, etc. So this would be their velocity times time minus length. The velocity times time is the center, and the velocity of time plus the length is their nose there. So it looks kind of like this, where all these diagonal lines in here are those computations. And I later added photon rings for when a body is in a place that it emits a signal. And then when I started, I just did a brute force computation of how long each of these lines would take to approach. And as the frame clock was greater than the time being observed, I could mark this is where the body appeared. So we get an equation kind of like this, that the time that an event is observed is the time that it was emitted plus the delta time it took to get to the observer, which is d squared, because this forms a right triangle, plus their velocity times the time of emission minus the length. So we're considering just this point, or the middle point, or the front point here. The positions of these along this time axis doesn't really matter. It's kind of a bad drawing. So we can consider this, that the time of observation is the time of emission plus a delta time. And if we can simplify this sum and say, well, the distance to the observer is 0, and the length of the object is 0, then we can simplify it to this. And this square root of something squared is just velocity times the time of emission, right? So we get this equation, time of observer is 1 plus v over c times time of emission, or time observed. But that's not really right. And this would have to at least be the absolute value here to be equivalent to this scenario. Otherwise, the sign of the velocity and the sign of the time are end up with a different graph entirely for this equation. It's kind of easier to solve this for just the delta time from the time of emission. And we could say that the time of emission is the time of observation minus the time of delta, or you can move the delta time over here, and the time observed is the time of emission plus the time delta. But we can substitute time of emission as the time observed minus the time delta, which now we need to solve for what time delta is and move all those terms over. And if we expand this, just this outer expression, we get velocity squared times this time squared plus 2vl times the time plus l squared, all over c. And then if we move the c over to the left and square both sides to get rid of the square root, then we can say that c squared equals t delta squared. c squared times t delta squared is this. And then we can expand these terms even further. So this is the longhand expansion of all of those terms, including this time delta squared, where it becomes v squared times time observed squared minus that 2 times that plus v squared times t delta squared. And to simplify this, we can take out all the terms that are the time observed or don't have time in them and just call it p. And then substituting that into this equation, we get a slightly simplified equation that just has t delta terms and this p. So we can move all of these terms to the left and combine these two delta terms, 2 t delta terms. I need to take a break here and consider that we have an ax squared plus 2bx equals 0. And there's another term here that we don't know yet. If we say that capital A is the square root of a, so that we can just have ax, and b is this b over the square root of a, then we can get an equation like this that's ax squared plus b equals c. And c turns out to equal this b squared over a. Or if we substitute these a and b and c back into this equation and expand it out, then we get ax squared plus 2 square roots of a times b over the square root of a plus b squared over a. And then these square roots cancel out, and you would end up with this ax squared plus 2bx. I missed an x there. Plus this term squared is b squared over a. And that's what c equals. So in this equation we have a c squared t delta squared and a v squared t delta squared. So this is c squared minus v squared. And then these are just t delta terms. So we can pull out this 2v t delta and this a term. So we end up with the square root of c squared minus v squared times t delta plus v times this term divided by the square root of c squared minus v squared equals p times this term squared, which is v squared plus v squared t observed plus l squared. And if we expand that out and take the square root of both sides to get rid of this squared term, then we'll end up with just one t delta term. And then this is the p term that we defined earlier that we can substitute into the equation and get back this. Okay, I did more work here. I also multiplied this by c squared minus v squared over c squared minus v squared. This term times p plus this term all over that. So then these two terms can add together underneath the radical. And that's where we were. So now we end up with t delta equals this expanded out actually ends up with two terms here that cancel out because you have a plus and a minus and a plus and a minus and a plus and a minus. So you'll end up with just c squared minus v squared times d squared plus c squared v squared, time observed squared. And if you multiply the top and bottom also by this square root of c squared minus v squared, that'll make this just c squared minus v squared, and this just c squared minus v squared, and then these two terms carry out and become this over c squared minus v squared. And in the end, we end up with t delta plus and minus this square root minus this. At velocities greater than c, you also have to consider the negative velocity, because this term ends up being able to have a positive delta. There is one thing, that this t delta must always be positive, because this is the time after the time of emission. You can't observe an event before it's been emitted. So this is a nasty bit of math that ends up giving you how long it takes for a signal to travel from any point along here. You can substitute in plus or minus L. Or 0, and compute from some time that you want to know if you've seen it. You can work backwards to where it was emitted. Now, I'd like to take a break and consider what is a relative velocity. If there's a train going 55 and a car going 65, and the car is behind the train and passing the train, and really we'll just consider where the engineer is. As the car is moving towards the engineer, he's actually got a negative 10 miles per hour relative speed. Once he's past the engineer, then he'll be moving further away, and his relative velocity to the engineer will be 10 miles an hour. And right as he's passing the engineer, their relative speed towards each other is 0. And you can make a graph of this, that this is how far away the object is, or the one body is from the other. And so you have a negative velocity that approaches 0 and then goes back up to whatever the positive velocity is. If there was 0 distance between the car and the train, and they're right over each other, then there would be an immediate step value between approaching the engineer and passing the engineer. And before I get into the 3D math, I'd like to first consider some simple vector math. So you have a vector that's defined with multiple components that define a position or a velocity or some related set of coordinates. The magnitude of the vector is the square root of all the terms squared and added together. You could also consider this as a dot product, where each term is squared is multiplied by itself and added together. And then that's actually, x squared plus y squared plus z squared. So the magnitude of a vector is actually the square root of the dot product. Or we could say that v times v is v dot v. This is just a convenience notation because I'm doing a lot of multiplication of vectors later. And this is the magnitude of that vector. Is that vector times itself. The square root of it is the length of the vector. And two vectors added together, each component is added. These result in a single number. This is not a vector. result. Whereas if you add two vectors, you end up with another vector where each of the components is added together. Or subtraction, each of the components is subtracted from each other. And a vector times a scalar, that scalar is just distributed through the vector. So we can go back to defining the math for 3D. So we have a position that is being observed from, a velocity of the observer, and the time that an event is observed. And from that we subtract the position that an event was emitted, a photon was emitted, plus the velocity of the emitter times the time that the event was emitted. So the velocity, the distance of the magnitude of this is the amount of distance that light has to travel. So if I divide the distance by c, that gives me a time that is the delta time from the time of emission to the time that it was observed. And this is another way of saying that, you know, the magnitude is the square root of that vector squared. We can define a p that's sort of like a displacement factor. It's the positions, it's position minus the position, plus other time variables that are not the time emitted, because we're going to solve for TE. So we get a more simplified equation that's time observed is the time emitted plus this delta time, which is the position minus the velocity of the emitter times the time of emission. And we can multiply both sides by c and move the TE over. So we get TO minus TE times c. And then we'll square both sides to get rid of the radical and expand this term in here, because we need to take these TE terms, the time of emission, and move it over to the left. And if we expand this left term also, because we end up with terms that are just time observed, then we can move the time observed over with the position, and these other two terms over to the left, and you end up with basically c squared times the velocity of the emitter squared times the time emitted squared minus 2 c squared, a time observed, the position times the dotted on the velocity times the time of emission. And we'll have to go back to the solving of the perfect square, and so we'll end up with square root of the a term, this b term, and divided by the square root term, and we'll end up with this squared on the right side. It could be that you subtract this term on the left already, so that the result is immediately 0. But we need to move it over to the right side anyways, so we can just add it to the right side. Then we take the square root of both sides, and then move this term over to the right because it only has time observed in it, and divide both sides by the coefficient of time emitted. And this is basically our solution. But we can simplify this sum because this square root term squares this and makes it just c squared minus ve squared, and carries into this, so that you end up with also with just this is a square root of this divided by the square root of that, so this ends up being again just c squared minus ve squared. And we combine terms under here So this is this term times c squared minus v squared, and the leftover term. And then if we expand all of this, we end up with a couple terms that cancel out, because we get a minus ve squared p squared and a p squared ve, and c squared t0 cancels out with a positive c squared t0 squared, t0 squared. And then we can combine these remaining terms. They all have a c squared in them, so we can pull that c out and get left with that. And then this ends up being a perfect square also of p minus VETO, velocity of the emitter times the time. And then we have, so this is that equation, and this is the p. So we substitute the p back in, and we get something like that. And this ends up being basically our final equation, massaging these terms a little bit to get a vector. A vector times a vector, so you get a scalar, and then c squared minus VO squared, VO times VE times the time of the emitter. And then, so this works for any 3D, 4D, 5D sort of equation. I really only went into three dimensions on it. So we should consider what length contraction is. I implemented a different version of C, and I call it C length. That's C times 1 second, so that the units of this is meters, and whereas the units of C is meters per second. So to travel a distance of C going forward, this is the time of the worst case. So this is the average of the time forward and the time backward along a velocity vector, which these multiply together. If you multiply this side by c plus the magnitude of velocity and this side by c minus the magnitude of the velocity, then you end up with c squared minus v squared on the bottom, because these are a plus and a minus. And the top terms cancel out, and you end up with 2 times the speed of light plus a length of light. And this 1/2 cancels out, removes the 2. So this is the worst case time that a photon emitted forward and then going backwards will take. And the best case time is formed off of the triangle. That's if you had a photon clock that was bouncing light up and down across a c length, then that divided by c squared minus v squared is what the best time back and forth would be. I guess it's really just one direction in this case. So we're doing a two-directional speed of light here, whereas this only requires a single speed of light calculation. And if we take the time of the best, if we take a time and divide by the worst time and multiply by the best time, then that scales that time to be the best time. And so you take these two terms, that's the time best and the time worst, divide them out, expand the fractions a little bit, and then you end up with a contraction term that is the square root of c squared minus v squared over c, or you could carry this into this, and this becomes c squared over c squared minus v squared over c squared. So this is 1 minus v squared over c squared, which is the inverse of gamma. Usually gamma is 1 over this. So this is a capital gamma that I'm using for the contraction term. To apply length contraction to a vector, you would take the dot product of the position along the velocity. That gives you how much of the position is along the velocity. And then scale that just in the direction of the velocity. And divide by the magnitude of the velocity squared. Because you end up with a magnitude here that you want to normalize this to a unit vector. And you really want to just dot product the position across the direction of the velocity. And you end up with the old position minus the amount of the position that's dotted on the velocity, and then add back the length contracted version of that on the velocity to give you the real position. And then this can simplify into 1 minus capital gamma. And light aberration, as you go faster, the light that you see is advanced in angle. But also, the faster you go, the light that gets transmitted is advanced in angle. This is an emission spectrum from synchrotron radiation, where this is a high-speed electron that's going. So most of its light, most of its photon transmission is beamed forward of its velocity. And this is basically the existing general equation that Einstein wrote for relativistic light aberration. And this is a delta position, so from the position of the emitter to the position of the object, like if it was along this line, you'd want to know what the direction is. So you can take that direction and dot it on the velocity of the observer and get the directed distance of which direction this light was coming from. And that gives you this cosine theta s term, the angle of the source. And the change in the angle is the arc cosine of this, basically. So J is this cosine theta term, and the velocity of the emitter minus the arc cosine of J. And that gives you the change in the angle and how much is advanced. Depending on what you're doing, you the arc cosine only returns 1/2 of this. So you have to consider that if the angle is coming from down in this direction, that there's a basically a modulus operation you end up having to do to get the actual angle that the light would be deflected forward. And this is all a mess. I just kind of threw this in from the paper. So we have again the delta position. This is the cross product of the angle emitted with the velocity of the position velocity of the observer. The cross product gives you the axis of rotation, and we can normalize that cross product and get a unit vector that's in the right direction. And then this is the velocity of I'm not sure why this is d. Oh, it's dot. So this is the velocity dot product and the normalized dot product. So we have the normalized dot product is the cosine, and the magnitude of the velocity over c terms from before. Magnitude of the velocity over c. And then this is the rotation formula for taking the original point. This is the observer. So it's rotating around the observer. So it's offset from the observer. And then the dot product and the cross product turning into this x results vector. This should be a vector. And the time contraction is similar to the length contraction, where we can take the length contracted speed that's forward and backward. These should be magnitude. And get c over c squared minus v squared, which is actually the inverse of gamma. Or we can consider just from the triangle and the photon clock what the time dilation factor is. And that's it. I would like to walk through some of these demonstrations. This is the original demonstration that I worked on that has a body that's traveling faster than the speed of light. Like the wavefront of its original wave can't even keep up with it. So what happens is you don't see anything until it passes you, and then there's two versions that I'm drawing. This one's the brute force calculation from checking the time of the photons going down the line, and the top one is the actual calculation. So then this shows the time color of what I'm actually seeing when it's hitting. Like this is just the front and the middle. The back hasn't actually even been seen yet until there. At which point the ship that you're watching is already well past where you are. And then as time goes on, you have one version that goes backwards and the other version that goes forwards following the body. Now there's the triangles are directional. So at the front of the ship there's a triangle going this way, and at the back of the ship there's a triangle going this way, and the middle is a diamond. But here the back of the ship is actually seen as the front of the ship going away. So it looks like the ship is
actually flying away from you. Although not really, because if you consider that was a three-dimensional object, it's like the image is inverted, because you wouldn't actually see the engines on this side of the ship as the back of the ship. You would just see the edge of the ship, and then the nose of the ship you would sort of see going away from you too. It's kind of bizarre. The next demo is limited, so the velocity is a max of the speed of light. Actually, 0.9999 times the speed of light or something. No, maybe it goes up to... but something I noticed with this is that as the ship is approaching you, it's actually elongated. Like, it's much longer than the ship you are actually seeing until it passes you, at which point it becomes contracted. And this is factoring in Lorentz length contraction. Like, the ship is usually 1 light second this way and this way, but it's at about half of its distance right now. If I increase the velocity, the actual length of the ship goes down. But regardless, the ship you see passing you is shorter than when it's approaching. And approaching, it can be very, very elongated. Less so there, or appear elongated anyways. So there's an animate option that you can stop it from going forward, and then you can check like where these colors are, that they line up with the circles and everything. The circles are an independent calculation from the arrows, which are going down the line at a specific rate, and a different calculation than the reverse calculation from this. So it's basically 3 calculations that end up all aligning to show this product. This is a slightly different version. I was figuring in the light aberration too, because this is a fast-moving observer that's passing past the stationary body. I can kind of shrink that some. So what the ship is seeing is actually directed forward from where it actually sees it because of the light aberration. But this is I can increase the distance, and this can apparently go faster than the speed of light too. But no matter what, a stationary body is always seen in its original position. Its length doesn't contract. Only the space of the ship can actually contract. Although it does appear elongated and contracted because of the light aberration going as it passes by. This version is more like taking the space that one ship is in and its grid of coordinates. So each grid is a unit of 1 light second. And if I... Right now, the observer and the observed are going at 0. If just the ship is moving this calculation seems wrong. The other one that turned out really good is this one. It doesn't always load right, but I have this 3D world that's a cube that's made up of 32 by 32 by 32 voxels. And on the left side is an orthographic view. The only difference between these two views is the camera, that this is using a perspective camera and this is using an orthographic camera. So in the perspective camera, from this previous test, I had kind of wondered if I divided the length by the position seen, because this is so much further away, this would scale the points closer, and then what would this actually look like? But in 2D, this would just project to a circle. And I'm not very familiar with circles, but with this, I can still show the orthographic view, which is essentially what this view is, and a perspective view of that same world. And it starts off with a locked velocity. So as I advance the speed, and I'm still moving along with the cube, my perspective of the world in a perspective view doesn't change. But this this is forward, and it's contracted to towards the viewer. So this large green patch that's seen is actually this small green patch that's here. And that gets bigger and bigger and bigger. And I can change the direction. And there's minor differences on this shading because that's such a small view. But basically the squareness doesn't change, even though the pixels are shifted by as if the light propagated from a point. Like when you're traveling, this is essentially a 3-4 light second long thing. So as you're traveling at almost 80% the speed of light, what you see of the forward ship is seen from a more recent time than the ship is actually at. Whereas the tail of the ship is, it takes a long time for the light to actually reach you from the back of the ship. So this is translated for the points you would actually see traveling along with the ship at that velocity. And I don't know, I can end up skewing this a little bit because of the time offset. But I can turn off length contraction and the light delay and aberration independently. So there's basically no translation possible here. This would be just length contraction. This is essentially the Lorentz transform in one direction, that things become elongated and shortened, and the light aberration is actually the inverse of that. So when they get combined, then in perspective, everything is still square. This is a little more confusing on this orthographic view, but I can turn on transparency so you can see the whole cube and actually fly into the cube and even approach this front wall. But then that front wall is actually bulged in closer to you. Well, which way is front? So that's the front of the ship, I guess. And this is the same idea of an observer traveling along with the ship. These are light aberration cones. So if I'm some distance away from the ship, and I'm going, say, ahead of the ship, like this is my current viewpoint, then the ship would appear to be coming from further away, but then it's advanced by light aberration to come back forward, and then in perspective it should match basically its original viewpoint. But it's having problems getting this math to be quite as square as this. This was actually quite astonishing that I could get this to actually be so very square at any velocity. So basically, if you were standing along in this room, the only way you could tell is if you had some strobing lights that cycled at nanoseconds, 1 foot away and stuff. This is set up to be that each color changes from red to green to blue once a second. So this is actually only 2 and apart light seconds long by how it's scaled. But basically one unit of this is probably 1/10 of a foot, so about an inch. So this cube is actually really, really small. But I'm right up next to it. And these aren't really showing. Oh, yeah. I don't know. Moving on. This was one of the final tests that I did, is this light interferometer. So if we turn off animation and start with this at the beginning, then this is your basic light interferometer, that a light is emitted from here, hits the splitter, gets split this way and this way, comes back, and it results in this final view. So there's initially this wavefront is together and hits the splitter. Then the red and white circles are still pretty much aligned, but these are the leading photons, and one wavelength behind them. I was kind of trying to show how they were length contracted. Like these other photons all look like they're going straight, but they're still following the same sort of trajectory. And then the back bounces off and comes back forward. But now these nodes in between are very compressed, and this is blue shifted. This basically doesn't have any frequency shift to it. And then they both meet back at the center splitter at the same time and proceed to go forward and hit the front detector. And I can change the angle of this apparatus. No, angle is something different. I can change the direction that the apparatus is traveling, which, if it was moving this way, then from the beginning these are blue shifted until they hit this middle, and then they're back to a little wider phase here, but continue to be red shifted that way. And then when it bounces off of this, the blue is a little hard to see mixed in with the red, but there's a wide gap in between the blue photons that are going that way. And again, it goes and hits the reflector. And I added up the times that it would take. It's not really the distances, but the time over the whole apparatus moving ends up being exactly the same for the two arms, no matter what direction you are. So the local clock here says 2 seconds. Always. And I can like increase the distance, and the length contraction becomes more significant. And still it's 2 seconds, and it comes back and it interferes with itself. I was also playing with just this light aberration phenomenon and frequency shift. There's a Doppler shift in this too, and depending on the angle, depending on the angle that the aberration is seen from, it has a different amount of aberration, which is kind of more important in the Galaxy version. Where basically this is meant to be a spinning galaxy. Oh, this is the Galaxy version. So in this, turn this speed down a little bit, I guess. Then if the rotation rate was a certain distance, then you would see a red shift on one side and a blue shift on the other. And I was trying to figure out if, just because of the aberration of these stars moving faster and then seeing a different side of the star, if that would account for the rotation curves being goofy. But there's more to it than just aberration. And I did another one that this is more along the lines of a Lorentz transformation, where I put up a bunch of different clocks that could be seen, and the ship and everything. So this was also a homework problem, that an alien is eating breakfast in the Andromeda Galaxy at the same time somebody on Earth is eating breakfast. And depending on where this ship is along this distance, they can see the Earth event happen first and then Andromeda, or they can see the Andromeda event happen first and then the Earth event. And if they're going very, very fast, then that offset kind of matters even more. If they're right in the center, then it's possible to see the events happen at the exact same moment. But if they're offset towards Andromeda, then they're closer to that side, and they would get, did I lock offset? Yeah. Then they would see Andromeda time happen first. And then the blue and red is not really sure what they represent. Kind of a time span of the breakfast, I suppose. But that doesn't work because it's offset in the other direction. So which option was that? Show distant frame. So if we go back to, well, we'll just reset this. So what this is showing is the velocity of the ship can go up to a maximum of, well, the speed of light. So that's this 45-degree angle. And the observer, an observer, which is this blue line, can also go positive or negative the speed of light. And then I'm able to show various clocks that are happening. Negative times are failing. Distance, half length, event time. Oh, this event time must be when the event actually happens. And an overall. Oh, this is a transformation between the observer and the observed. And whether it's showing from one perspective or the other. So, according to the local time, because the observers, because the clock on the ship contracts, then the ship is actually traveling faster than the speed of light. It's going this velocity for sure, and it can't go faster than the speed of light. But because the clock that's on the ship is going slow, they cover more distance in a longer amount of time, or the clock doesn't tick as fast, so the distance they cover doesn't take as much time. And that can go all the way up to like many times the speed of light. At 707 square root of 2 over 2, then their local velocity, it seems like the speed of light, because they're going 0.707 forward in 0.707 seconds, and therefore are going the speed of light, even though they're actually traveling slower than the speed of light. And that keeps doubling at 8601. That's like 2 times the speed of light, or 3 times. So this slope, this is like 4 times the speed of light at 9720, all the way up to actually many times the speed of light. This looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, or about 10 times the speed of light. Relatively, because their clock is ticking slow. Not that they're actually going 10 times the speed of light, although effectively they are. If they traveled at 0.996% the speed of light, or 0.996 times the speed of light, then they would be traveling 10 light years in only 1 year of local time. And that's an entirely different topic that should be covered. And then this was a wheel traveling at the speed of light. And there's and this is just as it's seen. It must also have length contraction. I guess I set C as 3 for some reason. And this is all done by brute force, that all these points on the wheel are calculated independently. Reverse calculating the arc sine and arc cosine of where the wheel was when it was at some frame in the past is just impractical to do. I have another variation of this that this is more if you were traveling inside the wheel and the wheel is spinning around you. I don't know. That's all the interesting demos, I suppose.